So we are on page 130 now. If you're starting fresh here. Multiplying the complex numbers. So this is where things again get a little weird. We have to use the fact that I squared is equal to -1. So it's going to make our solutions just part of the real set, or the complex set, sorry. So we use the distributive property, we FOIL. So we take the first terms, 4 times 6 to get 24. We take the outside terms, 4 and -2 to get -8i. Inside terms, 9 and 6 to get 54i. And then the last terms, 9 and -2 to get -18i squared. So now is where we say, okay, I squared is the same thing as -1. We take the real portions, so we got positive 18 now and 24 to get 42, -8i and 54 to get 46i. So we try another one. We distribute. -3 times 7 is -21, minus 12i, that's our outside terms. Inside terms, 12 times 7 is going to get us 84i, and then plus 48i squared with our last terms there. So our -21 isn't changing, our 84i isn't changing, but now we've got that 48 times -1, so that gets you -48 combined with a -21 to get -69, and then with our I terms, -12 plus 84 would get us a positive 72i. So is the product here a real number or an imaginary number? Let's take a look. So our inside terms, first term, a times a gets us a squared. Outside terms get us -abi. Inside terms would get us positive abi. And then the last terms would get -b squared I squared. Well, our middle terms are going to cancel out. Our I squared is going to be the same thing as -1. Our answer will get a squared plus b squared. So since those are both real numbers, we will just get a real solution. So let's do some multiplying. So first terms, 6 times 3 is 18. Outside, minus 60i. Inside, minus 15i. And then the last terms, plus 50i squared. So I go ahead and in this step, I combine my i's already. Now I say my I squared is -1. So now I take the -50 plus the 18 to get -32 minus 75i. Over on number 11 here, first terms, 8 times 11 is 88. Outside terms, plus 8i. Inside, plus 165i. And then the last terms, plus 15i squared. I do my inside addition here, 173i. I change my I squared to -1. So 88 minus 15 will get me 73 plus 173i. So we can actually use these in talking about electric circuits. I actually did these in college. So there's some types of components that have different symbols in a circuit diagram. There's a resistor. So when we talk about a resistor as a complex number, it's just going to be a real number A. That's the resistance it's applying. The inductor here in the middle is going to be imaginary number BI, where the B is greater than 0. And then the capacitor is an imaginary number BI, where B is less than 0. So this diagram of an AC circuit is shown along with the impedance, which is kind of the total resistance of each component in the circuit. The power source, which is on the left, is labeled 120 volts, and it causes electrons to flow through the circuit. So impedance is the measure of each component's opposition to the electron flow. So if we look back up here at our table here, at all of our different pieces here, this is a resistor. So it's got a resistance of 4. This piece over here is our inductor. So in its imaginary number, this 3 represents the B. So it's 3I. And this capacitor here, since, with the inductor, B has to be greater than 0, so that's why it's a positive 3. And then our capacitor here, B has to be less than 0, So that means it is negative 5I. And we'll see that down here. So the total impedance is the sum of the impedances for the individual components. So again, for the resistor, we said it was 4, inductor 3I, and for the capacitor, negative 5I. So the total impedance, we add them together. So basically, you're just mostly adding those imaginary parts there to get a total impedance of 4 minus 2I. So Ohm's law says that voltage V is the product of the current I and the impedance Z. You will more often see it in college if you take any electricity or magnetism courses. V equals IR. It's one of the really important equations you have to know. So for this given current, they're telling us, for this given circuit, they're telling us the current I is 24 plus 12I amps. So if we want to find the voltage for each component, that's our V we're looking for. We take our I, which is the same for each of the components, multiply by the impedance of each piece there. So we said for the resistor, it should be 4. So if we multiply 4 times 24 is 96, and then 4 times 12 be 48I. Voltage for the inductor, again, we take that same current, we multiply by its impedance, which is 3I, multiply here, we'll get negative 36 plus 72I. Notice here, this has now become a real part. 12I times 3I will get us that negative 36, and the 3 times the 24 is what gets us the 72I. And the last one for the capacitor, we said was negative 5I. Again, you have to be careful here. So if we take that 12I times the negative 5I, 12 times 5 is 60, negative 60, but then we have the I squared, which would get us another negative 1, which makes that positive 60, and then the 24 times the negative 5, you get the minus 120I. So what kind of number is the sum, difference, or product of two complex numbers? They're all complex. They're all complex. When is the sum of two complex numbers a real number? When the imaginary parts are opposites and add to 0. That means imaginary parts are going away, you're just left with the real. Similarly, when is the sum of two complex numbers an imaginary number? When the real parts are opposites. So that way they add to 0 and you're just left with the imaginary component. All right, last page here. What are the similarities and differences between multiplying two complex numbers and multiplying two binomial linear expressions? So when we had the linear product, we had a trinomial quadratic. So something like ax squared plus bx plus c, whereas when we had the complex product, we came up with a complex solution, ax plus bi, or something like that, or a plus bi. So how do we add and subtract complex numbers? We combine the like terms.